moving on with proceedings, it's with the greatest of pleasure that I will introduce you to our keynote speaker, Adrian Bowyer. Many of you probably already know Adrian as the grandfather of the RepRap movement, but for the uninitiated amongst you, Adrian has degrees in mechanical engineering, which he got from Imperial College before then studying tribiology. He then moved to Bath University to the maths department before then bridging over to engineering. And amongst the RepRap movement, he is also credited with one of the creators of the Voronoi diagrams. And I know I, on a personal level, make prolific use of those almost daily. I think Adrian is our only speaker as well who has been awarded by the Queen, Her Majesty, with an MBE as well to his credit. So we really do have pulled out all the stops with our keynote speaker here. But again, I probably won't do you justice describing all of your accolades. So I will hand over to you, Adrian. Thank you.
Thank you. Thank you very much. I don't know, how can I follow that? Thank you for inviting me to speak. The title is The Mass Proliferation of Open Source Hardware and Additive Manufacturing and the Future of Open Source Innovation. That's the last time I'll say additive manufacturing. It's going to be 3D printing from here on in. So anyway, I thought I'd start with a little history, and this is perhaps an echo of one of the slides that Fabio showed earlier on. This is human history, all of it. As far as we know from paleoanthropologists, human beings evolved about 300,000 years before the Common Era. They keep pushing that date back a little bit, but as far as we know at the moment, that's how long we've been around. And on these graphs, I've put a little sort of thing at towards the right-hand end to give some people some idea of scale. My name is Bowyer, which means I'm a maker of bows. My ancestors were, and I come from a long line, therefore, of armaments manufacturers. And quite how long a line you can see there, because that goes back to 50,000 years ago. Anyway, this is a rather unhappy graph. As you can probably guess, it's an extrapolation, but the blue line at the top is the percentage of humanity living in absolute poverty. The orange line at the bottom is the life expectancy of a human being on Earth. And neither of these numbers are great. Now, of course, 250,000 years ago, the United Nations weren't gathering very many statistics on this sort of thing, but we can be reasonably confident that at that time there wasn't some magic golden age where people were living in sybaritic luxury in the Elysian fields. Things were pretty poor right back from the point where we did start to gather statistics. The life expectancy of 25 years there, of course, it doesn't mean that everybody was dropping dead at the age of 25. It's a highly bimodal distribution. And so what's happening is that half of people were dropping dead at the age of 50, and the other half were dropping dead at the age of 0. Anyway, if you look at the extreme right-hand end, you can see that recently we started to get some things right, because those rather unfortunate statistics start to improve. And the first time I heard about this and saw it, I thought, oh, well, that must be the invention of agriculture. Suddenly we had much more food available. So if we compress the graph a bit and just look at the right-hand end for the last 12,000 years ago, that shows us what happened since the invention of and it wasn't agriculture that caused the improvement. Unfortunately, people were still living in pretty much the same situation after they ceased gradually, of course, to become hunter-gatherers and started farming. So, well, the obvious next question is, well, was it the invention of machines that allowed us to slightly avoid the hard graft of everyday life? And we've had machines for quite a long time: seagoing ships, windmills, water mills, and other devices like that. Plows, of course, say for about 2,000 years. The right-hand end of the graph there. So, if we look at machines. No, those didn't make the improvement either. Things are getting a little bit better, but not very much. And so again, we're going to concentrate on the right-hand end of the graph and see what caused the considerable improvement, which at least is now clearly visible, as you can see. And so what really made the difference was the Industrial Revolution, not the fact that we started to use machines. We've had clocks for 400 or 500 years, for example, quite complicated machines. But the thing that really made the difference was when we started to use machine B to make machine A, as opposed to machine A's all being made, as it were, in a more or less custom manner by a human being working with very straightforward tools. And we have really made quite significant improvements, both in poverty and life expectancy. As you can see, the poverty graph has gone down from over 90% to around about 9%. Now, clearly that needs to be improved yet further, but nonetheless, we should at least take credit for having achieved quite something momentous in the last 200 years in that regard. Similarly, life expectancy, as you can see, that's going up, the orange curve. That orange curve is going up to a certain extent because people are living longer, but the real reason, the thing that's really driving that, is the reduction in infant mortality. Now, by fairly common consent, if you ask any human being what's the very worst thing that could happen to them, worse even than their own death, they'll say the death of their child. That's the thing that we've been conquering in the last 200 years, and particularly we've been conquering it during my lifetime. I was born just after 1950, and I've seen most of this improvement that you can see on the graph there myself. If you were to take anybody from history and, as it were, magically bring them forward to the present day, there are 6 words you could say to them that would cause them to fall at your feet in tears, asking you how on earth we had done it. And those 6 words are, our children don't die anymore. So we have the Industrial Revolution. It has created considerable reduction in poverty, a considerable improvement in health and life expectancy. Of course, it's caused problems that we're trying to address with greater or lesser success. But we shouldn't forget that even though there are those problems, the whole thing has been a considerable success for the vast majority of human beings alive. Right, so we've got machines making machines. To make a machine, another machine needs a recipe, or to use the precise, rather engineering-y term, a procedural definition of the thing that's to be made. But let's stick with the recipe because it's something that everybody understands. Now, that recipe may or may not come from a design. And we've got 2 examples here. Top left is something that many of you will recognize. It's an Arduino microcomputer, and that consists of a design, and what you're looking at there is a 3-dimensional rendition of that design. That design had to be translated from a design into a recipe in order, for example, to cut the printed circuit board out on a CNC machine. That recipe consisted of a load of G-codes for the CNC machine. The design consists of a piece of geometry that was used to generate those G-codes. Sometimes you don't need a design. So if we look at what's going on trillions and trillions of times as we speak in your own bodies, the construction of proteins, bottom right, we've got a ribosome, and that's building a protein by a process that I'm sure many of you will be familiar with. And there, the recipe is something that's in your DNA. That recipe is copied to a messenger RNA, which drives the process. There is no design there. It's all recipes. So the fact that we've got a procedure doesn't necessarily mean there had to be a preceding design. Now, both of these things are data, obviously. DNA has been around for 4 billion years. It's base 4 data, which obviously is easily turned into base 2 data if we want. The CAD design for the Arduino is also data, a string of 1s and 0s in the form that we're all familiar with. And in order to be useful, data has to be copied. The G-code that would allow us to cut the printed circuit board on a CNC machine, or indeed etch it with a photo etching process, would have to be copied to the CNC machine or the photo etch machine in order for it to actually construct the object that's been defined. Similarly, the person, you who's making a protein at the moment has to take a bit of your DNA, copy that to messenger RNA before that can be useful. And of course, human beings have many laws about copying data. We have the idea of copyright, which may or may not allow you to copy some data. We have the idea of patents, where a patent is essentially data. It's a document which tells you whether you may or may not make some device, which is also defined by data. We have various licenses, some of them open source, which is what this is about, some of them less so. We have the copyleft license, for example. We have all sorts of other open source licenses with which I'm sure you're familiar. So human beings have an awful lot of stuff about moving data around. In contrast, nature really only has one law about copying data. Here's a picture of Darwin's finches, which form part of his study into the nature of natural selection. Nature's law about copying data is Darwin's law of evolution by natural selection. That's what says what happens when data gets copied. Now, of course, the fact that something's natural doesn't necessarily mean it's good, but we can say, because it's been going on for 4 billion years, that at least it does mean that it works. So we know that it's got something going for it, even though we may not necessarily approve of the results from a moral perspective. That's something that's independent, orthogonal to what we're talking about when we're talking about the success of copying data. Okay, well, this is about open source, and I contend that open source design data is more likely to be copied. If we look again at a biological example, top left, and we'll come to the bottom right one in a moment, there's a clover which is having some data copied by a bee. The data, of course, is in the clover's pollen, and the bee is assiduously taking that pollen and taking it to another clover, which is what the clover wants to happen, because that's how the clover makes more clovers. Clover can't move, the bee can, hence the collaboration. Now, of course, the clover doesn't try and prevent the bee from copying the data. On the contrary, it goes to every possible extent that it can in order to encourage the bee to copy that data as freely as possible. It has bright colors. It even supplies the bee with a reward in the form of nectar for doing the task, and it tries to put as few impediments in the way of copying the data as is possible, which is, of course, the absolute reverse of what you do, for example, if you copyright or patent something. Similarly, the Arduino that we saw before is an open source design. Anybody can copy that design, though you can't write Arduino on it unless you come to an arrangement with the people who originated, but that's fine. So if we look at the copying of data that allows things to be made, in evolutionary terms, open source design data is fitter. Now, fitness here doesn't mean the ability to bench press 100 kilograms necessarily. What fitter means here is that it leaves more copies in the next generation. And we can see that with open source software, the growth in the number of Linux and Linux-derived systems in the world. We can see it with open source hardware. Joshua has already talked about 3D printing and open source 3D printing, something which I was involved in as well. So almost everything that people make, all those things are de facto open source. And the reason is because most things that people make have been around for quite a long time. Sure, you may have, for example, a registered design for a telephone or something like that, but the principle of a telephone, the idea of making a telephone, is not something that you can protect. Similarly, a refrigerator or a motor car or a shovel, corkscrew, clock, seat, spoon. Anybody can set up a factory to make spoons. And those things and almost everything else that gets made are not protected in any serious way by the sorts of rules that I talked about a couple of slides ago. We can imagine a world in which patents, for example, lasted not for 19 years, which they do at the moment, but for many, many generations. And if that were the case, it would be extremely difficult for people to make all of these common everyday objects that you can see before you. And the people who had the whole idea of patents and have framed the legislation and so on have tried to strike a balance between rewarding the people who had an idea and also allowing other people to take advantage of that idea after a reasonable period of monopolistic advantage has expired. And so almost everything, as I say, that we make is de facto open source. And of course, what this means, as a point that's already been made today, is that you don't need any form of protection of a design or an idea or an invention in order necessarily to make money from it. To repeat myself, anyone can set up a factory to make spoons, and if you make an efficient spoon making factory, you can sell those spoons to online retailers, to high street shops and all the rest of it, and you'll make a profit. You won't make an enormous profit, but you'll make a profit which allows you to employ people and to live a comfortable life if you do it properly. And similarly with almost all the other products that we buy on the market in everyday life. Now, turning for a moment to 3D printing, which is one of the subjects that is, if we like, an enabling technology for making things. I just thought I'd go back in history again, and this illustrated on the screen here is the very first public appearance of the idea of 3D printing. Now, I say public appearance, in fact, there was a single patent that predated the 3rd of October 1974 by Wynne Kelly Swainson for essentially the same process that I'm about to describe, but that patent wasn't published at this date. So as I say, this is the first public appearance. The first public appearance was in the magazine New Scientist, and you can see the cover there for the 3rd of October 1974. It actually shows the Nobel Prize winning ceremony for that year. But at the back of the magazine, at the opposite end of the cover, was a column written by David Jones, sadly now dead, under the pen name Daedalus. And that column used to be a humorous invention of some sort every week. And interestingly, quite a few of those inventions actually turned out to be practical. Some of them didn't. For example, he had the idea of a very large, very light boat that would float on the top of the clouds, or a democratic bus that would have a steering wheel for every passenger, and the bus would drive the route that was the average of the position of all the steering wheels. Now, you can imagine what might happen with that when the road came to a fork. But some of his inventions really did turn out to be extremely prescient. For example, he invented the idea of noise cancellation, the idea that you could take the surrounding noise around a pair of headphones and feed them an antiphase into the headphones in order to cancel surrounding noise and produce a quieter environment for the immediate vicinity of the ears than would be the case just if they were unsurrounded. He also invented the idea of the fullerenes, that's to say carbon molecules that consist of carbon in, for example, the shape of a football, the C60 molecule, which subsequently won the Nobel Prize for the person who actually created them. But Jones was the first person to think that these might be possible. Anyway, on the 3rd of October 1974, he came up with an idea of shining a laser through liquid monomer, which was designed to set in the presence of light. And he said that you could use this to weave all sorts of patterns because the laser light as it went through would make a straight solid line in what was otherwise a liquid. And so you could use it to sort of do three-dimensional knitting. And then he extended that idea to say that if you set up the chemistry just right, you could actually make the liquid monomer solidify only at the point where two beams intersected, which would allow you to define a point in space. And you could then trace out the volume of a solid object by deflecting the lasers and produce a three-dimensional object with no intervention other than the original design for that three-dimensional object. Anyway, as I say, that was the very first appearance of the whole idea of 3D printing, and not quite the way that SLA was implemented early on, which was one of the first processes, but nonetheless close enough to be clearly an ancestor of it. If we move on to the present day, then we've got 3D printing in 2022. Large numbers of companies have been set up on the basis of the RETRAP project and other research, of course. This is Joe Prusa's warehouse, or rather a very small part of it, where he has a very large number of RETRAP machines making more RETRAP machines. So going back to the Industrial Revolution, where we had machine B making machine A, and that was the thing that allowed us to produce all those improvements in the human condition, we now have got to the point where we have machine A making machine A. These 3D printers, they are RepRap machines because they're 3D printers that reproduce themselves. These 3D printers are making the parts for more copies of themselves. And of course, they don't just do that. That would be an intellectually interesting achievement if that was all they did, but they're also capable of making a very wide variety of other products in addition to themselves. So we now have self-reproducing machines and also people making 3D printing machines using conventional production technology as well. And these are very widespread all over the world, as you're all aware. Right, now, once we've got a 3D printer that's open source, what other manufacturing hardware can we derive from it or produce in parallel to it? Well, top left is the thing we've just been discussing, the RepRap machine. That's a little design of one that I made and have been working on, as it were, in the background. There are many, many hundreds of other designs for these machines out there now. Laser cutter, another standard piece of manufacturing equipment. I apologize, incidentally, if the examples I choose are not your particular favorite. There are many other open source versions of many of the things that I'm going to talk about. I've just plucked examples almost at random from the lists that we all have. But the Laser Duo is an open source laser cutter that anybody can construct themselves. CNC milling, I've already mentioned in the context of manufacturing printed circuit boards. It's one of the two main ways of doing it. And there are open source CNC milling machines. There's the RS-CNC machine, which interestingly has many of its component parts designed to be 3D printed. So if you've got a 3D printer, you can also use it to make a CNC cutting machine, and to a certain extent, vice versa. And in particular, you can make a CNC cutting machine which is very large and compared to the 3D printed parts that go to make it up. And so you can actually make larger items on it than the 3D printer that printed the parts, some of the parts to go to make it. There are designs out there for open source lathes. Bottom left is a picture of a concrete lathe. Concrete is a rather useful material for making a lathe because you want something that's both very rigid and very heavy to reduce vibrations, and concrete is a nice, cheap, rigid, heavy material. And of course, in order to produce concrete in virtually any shape, all you need is molds, and it can all be done at room temperature. So we've got the possibility there for another type of machine tool, again, extraordinarily widely used, the lathe, and that could either be a CNC lathe or indeed a manual one, which could be easily made by anyone because it's, again, open source. Moving down in scale and looking at the manufacture of electronic chips, a number of people have looked at open sourcing electronic chip manufacture, and we'll come on to some of the software for that in a moment. But there's, for example, a guy called Sam Zeloff who has started making conventional chips in his garage. In 2018, he was at 6 transistors. In 2021, a year ago, he was up to 1,200 transistors. And he's looking at making, he's not strictly open source, but he does publish how he's done everything. So it's de facto open source. It's not under any particular license. It's simply a series of instructions which anybody could follow. And finally, on this slide, bottom right, there's the Buster Beagle 3D injection molding machine. Injection molding is an absolutely key industrial process. It does pretty much what a 3D printer will do, but much, much faster. This is a very simple injection molding machine that's based on a drill press, a very straightforward device, which most people have easy access to. The advantage of injection molding is that you can produce things at a much higher rate than you can in 3D printing, using 3D printing. The slight disadvantage is that it's more difficult to change the design. You have to change the dies or the molds that you use, which can be an expensive process traditionally. But again, CNC machining and 3D printing come to the rescue here because it's possible to make new dies using those technologies much more cheaply than can conventionally be done. So there we've covered a range of industrial processes for manufacturing things, all of which are open source or potentially open source. And in doing those, in open sourcing those things, we allow the manufacturer so much more. Just going back to the chips in a minute, there's a rather cheeky graph on Sam's page describing all this, where he shows Moore's law for industry. As you know, the number of transistors on a chip doubles every 18 months, 2 years, whatever it is. And Moore's law for the industry is the blue line here. Moore's law for Sam's garage is the orange line. So at least at the start, he's doing pretty well. Of course, he has the advantage that he's following something that's already known to be possible, which always makes things easier than having to invent something ab initio. Right. Now, it's no good having open source machines for making things unless there's a way to drive those machines. So we also need open source tool chains in order to take what we want to make and turn it into data that can be copied into the machine that actually does the making. And again, here are just some examples. There are many other pieces of software available that do similar things. We might start with a mechanical design and some free software like FreeCAD, and then that design, as I say, needs to be turned into a recipe or procedural model in order to actually manufacture it. FreeCAD, in fact, has its own path planning software in it, which will drive a CNC machine. Or, of course, if we want to 3D print the thing that we've designed, we need a slicing program. There are many of those out there. Slicer with a backwards 3 is just one of them. So we have a complete open source tool chain for taking CAD designs right through to the manufacture of those CAD designs in the open source tools that we've got. Turning again to electronics, we've got, I'm never quite sure if it's KiCad or KiCad. I have a nephew who calls it KiCad and I call it KiCad, and we look at each other askance, but anyway, open source electronics design software. And once again, we need to turn the design that we've done for the geometry of a printed circuit into a recipe or a procedural model in order to drive either a CNC machine to cut the copper away where we don't want it on a printed circuit board, or to drive a photo etch machine to manufacture it using etching technology. KiCad is capable of producing Gerber files, which is an industry standard definition for printed circuits. And then those Gerber files will go into programs like PCB to G-code, which will drive a CNC machine, or the Gerber files themselves will drive a photo etch machine. Moving down in scale to the individual chips, Google and Skywater publish an open source process design kit for doing chip design at 130 nanometers. That's completely free. And there are other process design kits for doing chip design out there as well. In addition, Google will sometimes even make your prototype if they think it's particularly interesting. They'll actually fab a wafer of 200 or whatever it might be of your design for you, though of course that's not guaranteed. They won't make everything that anybody comes to them and emails and says, can you make this? Or there's using the techniques that Sam has developed from industrial techniques in order to do the same thing, though to be fair, his systems are not yet capable of working at 130 nanometers. Okay, so we've got self-reproducing 3D printers. We've got an open source machine A made by a copy of it, or making a copy of itself, and that permits us to make different manufacturing machines from the same manufacturing machine, and this forms a sort of positive feedback loop. All of these machines can make parts for all of the other machines. We've got a sort of virtuous circle here of production that requires very little closed source material in order to make it. I'll come to one or two examples in a minute of things that we perhaps might need to bring in from outside. And once we've got the ability to do all that making, we can certainly make clocks. Indeed, there are many open source designs for clocks out there now. Pretty easy to make a corkscrew. A little bit more difficult to make a teaspoon. That wouldn't be impossible. I don't know if there's an open source design for an entire refrigerator, but certainly many of the components of it could be made using open source technology. And so what I'd like to go on to do is to look at how we can use this open source manufacturing technology to make useful stuff, either things that are being done open source now or things that we might do in the future. So let's start with a type of chip that is not itself open source, though in principle we could use the tools that I've just been discussing to make one, and that's a field programmable gate array. Many of you will be familiar with this. It's basically an electronic chip where you can actually decide how it's wired together after it's being manufactured. And there is plenty of open source software available for taking such chips and deciding how to wire them up. And indeed, there's an open source FPGA association devoted to standardizing and distributing such software to allow you to take your electronic design and to turn it into a piece of into an electronic chip using an FPGA. On the right is an example of the sort of thing you can do with this technology. It's an open source version of the old Amiga 500 computer called the Mini-MiG. And rather interesting thing here is that they've used an FPGA to mimic the old microprocessor that used to be in the Amiga 500, the Motorola 68000. Now, those of you who are involved in microprocessors, have been for a little while, will know that the 68000 was one of the nicest designs of microprocessor. It's highly orthogonal design, extremely intuitive. Once you saw the instruction set, it was very easy to sit down and write assembler for it. And this machine was the basis of the Amiga 500, as I say, but we can now get a Motorola 68000 made inside an FPGA, so it's the equivalent of the old microprocessor, and you can see that that's essentially quite a powerful idea. Okay, let's look at some other open source manufacturing technologies that we might come across, enabled in many cases by this technology. Open source genetic engineering. There's a recent paper in Nature by Hugh et al. On a complete open source tool chain for CRISPR-Cas9 gene editing of the tomato. You can use the tools that are available and described in that paper to genetically engineer tomatoes, and of course it's not a big step to go from genetically engineering tomatoes certainly to genetically engineering other plants. Tomatoes are plants where the genome has been particularly thoroughly studied, but there are plenty of others, of course mainly crop plants where the level of study is almost the same. It wouldn't be too difficult to adapt this to genetically engineer those. Now, open source genetic engineering is a bit of a two-edged sword. Of course we may use it to produce all sorts of improvements, but it also has the potential to engender all sorts of mischief. You can imagine some bad actors using open source genetic engineering to create things that we really wouldn't want created. You can buy a CRISPR-Cas9 kit. Now, this is not an open source kit. It's illustrated on the right from a company called the Odin. This is something that allows you to move genes between yeast and bacteria. But you can see, given the picture there, that there's nothing very much involved that couldn't be manufactured in an open source way. As I say, this kit doesn't have to happen to be an open source kit, but it would be very easy to make an open source genetic engineering kit using the sorts of technology that we've just seen discussed. Something else that's possibly very valuable to a very large number of people. About 1 person in 20 in the world has diabetes. And there's a project, openinsulin.org, underway to create a complete open source system for generating insulin that anyone may adopt in order to manufacture insulin either for themselves or indeed for commercial production. And if you look at the cost of insulin, unsurprisingly, it varies widely. Typical cost for a patient in the USA is about $500 per month. The National Health Service in the UK pays $40 per month for a patient. Of course, in the UK, the patient sees nothing of that. They get treatment for free. But looking at the developing world, people with diabetes in the developing world can be faced with bills of about $300 per month. And it's fairly obvious that in order to keep them alive, something needs to be done about that. And the idea of having an open source complete path to producing insulin is an extremely attractive one from the perspective of a significant fraction of the human race. Just a word about how it's made. It's made by genetically engineered bacteria working where you have a large number of these bacteria growing in a vat, and they produce insulin, human insulin, because they've had the gene for human insulin grafted into them. That's how it's commercially done. Also, I guess how the open insulin people intend to do it as well. Joshua has already mentioned the idea of open source laboratory equipment, and indeed I've taken the liberty of putting a picture of his in the top left-hand corner there. This is a bit of a challenge I'd like to give to all of you. Here's illustrated a fancy piece of glass blowing. It is quite fancy, but it actually costs £2,643.26. So the question you have to ask yourself, is that object you see before you something that you should really be paying £2,500 for? All right, it's got 5 ports on the top, or 4 if you've got one for temperature, and it's got a jacket around it for cooling or heating, and it's made of borosilicate glass and so on. Something that would be really useful, which perhaps you might like to consider setting to an ambitious PhD student, is an open source glass blowing robot that's capable of making this sort of stuff. Obviously, this wouldn't be the first thing to make, but nonetheless, a great deal of laboratory work can be done using the type of equipment that Joshua mentioned, which is essentially made of plastic. But for some laboratory work, you really do need glass. The fact that human beings have glass is the reason that we understand chemistry. It's the thing that allows us to do all the experiments, and indeed still does, that we need in order to develop the sorts of things that I've been talking about in the last few slides. So an open source glass blowing robot that was capable of making glassware where individual items cost rather less than £2,500 would be an extremely useful thing to have. And as far as I'm aware, I did do a search, such a thing does not yet exist. Okay, something else in the medical field is open source prosthetics. There are people set up to make prosthetic hands, prosthetic arms, prosthetic limbs. Most open source prosthetics are directed at people who've had a limb amputation of some sort. And there are various URLs on the screen there for organizations that do this. The slight distinction between openbionics.org and openbionics.com. Openbionics.org is genuinely open source. Openbionics.com don't publish all their designs. So they make quite a good 3D printed prosthetic arm and 5-fingered hand. So this is clearly something where open source has a great deal to contribute to the alleviation of human suffering. Large numbers of people have various disabilities caused by the fact that they're missing one or more limbs, and the ability to use open source techniques in order to help them in their lives is obviously extremely important. Open source agricultural robotics, this is something that I'm particularly keen on. The idea of automating agriculture is something that goes right back to the invention of the tractor, I guess, but nonetheless, doing it with robots which require no human attention is a very powerful idea. And there are essentially 2 ways of going about this. There's the type of robot you can see top left, which is a solar-powered robot that wanders around a field, planting plants, weeding between them, possibly harvesting the crop. So that's basically roams wild, as it were, except under control, but it can go as far as it needs to. The other approach is to set up a Cartesian robot over a particular area of land, as in bottom right there, and that robot then tends that area of land, watering the crop, again weeding it, harvesting it, and so on and so forth. And of course, there's a certain amount of well, I'll come to that in a moment. One of the advantages of both of these techniques is that you can have a mixed crop. You don't have to have a monoculture. Because the robot can distinguish one plant from another, it can go through every 3rd plant and harvesting that 3rd plant, which is different from the other 2. And of course, if you don't have a monoculture, it makes for a far more robust cultivation against disease and other problems than if you have a monoculture. As I say, vision discriminated harvest there, it's fairly straightforward to get a camera these days to recognize a particular species of plant, whether it's a weed or whether it's the plant you actually want to keep. And of course, these two techniques have a certain amount of cross-fertilization between them. The effectors that work for one will also work for the other. Open source buildings, there's the Wiki House, which is a house which is open source, which is made from cut timber, cut plates, cut sheets of timber, which are assembled, cut off site and assembled on site to make a highly insulated house for people. Again, completely open source design. Many of you will have seen lots of 3D printing machines that print concrete. They tend to be large Cartesian robots, but I think that the way to go with this is to use the hang printer, which was made by Torbjörn Ludvigsson. This is a machine which is a 3D printer suspended from a single point above with 3 anchor points on the ground, forming a tetrahedron which drives the print head around in space. You can see a column that's printed there. It's pretty obvious that you could use one of these for concrete printing, and that would allow you to just come up to site with a single tall crane and start building a building. Open source mesh networking, liberating ourselves from service providers. There are a number of projects around for creating open source mesh networking. Some of them just software, for example, is Bowyer, which is something that runs under Android, or there is a combination of hardware and software, that's to say the actual physical nodes as well as the software that drives them, so that people can communicate with each other without needing to go through any particular commercial company as an intervening medium. Very useful if you happen to be, for example, in an emergency situation where there's no phone coverage. If all the phones there have Bowyer loaded on them, the phones can talk to each other, which is a significantly useful thing. Open source electric cars, there are a number of projects for this. This is the Tabi electric vehicle chassis, which is intended to be an open source basis for making electric vehicles of many different kinds. And finally, open source fusion, just before I get to the end. There are a number of projects, commercial projects, to make a fusion reactor, which, once it's successful, will be an extremely important source of power, clean power, for humanity in general. On the left is a graph of the fusion triple product, which is basically the thing you need to have a high value of in order to make a self-sustaining fusion reaction. It's the density of ions in the fusion reactor times the temperature times the time it's contained. 40 years ago, people used to say it'll be 40 years before we have a working fusion reactor. And in the last 40 years, every journalist has made the little joke that fusion is always 40 years ahead. Well, here we are 40 years after people said in 40 years time we'll have a fusion reactor. And my estimation is that we're a few years away from it, but not too far. And particularly ITER project, which ought to be a working fusion reactor, which has a gain greater than 1, produces more energy than it consumes, is scheduled for 4 or 5 years' time. Plenty of home-built fusion reactors, not using the same principle as ITER, which perhaps, interestingly, once commercial fusion becomes greater than 1 energy production, greater than factor 1 energy production, that might trickle down into the open source home-built fusion reactors. Okay, I'd like to finish with actually my first slide, which seems slightly eccentric as it's my last slide. When I was asked to give this talk, I obviously didn't know what to say, so I consulted an artificial intelligence about what I should say. The artificial intelligence I consulted was Stable Diffusion, and the prompt I fed it was people making machines by open source innovation, patented by Artemisia Gentileschi, and Stable Diffusion came up with that image, which looks a little bit like a hackspace or a makerspace, possibly from a bygone age. So that's what the AI told me to talk about, and so naturally I followed its instructions. Thank you all very much. I don't know if we've got time for questions or not, but I'll be happy to take them if there are any.
Brilliant. Thank you so much for that talk, Adrian. That was really, really informative. Excellent talk. I always walk away feeling absolutely inspired every time I hear anything which has your name attached to it, and this is no exception by any means. We are slightly over, but as we have Adrian with us, welcome any questions anyone may have.
I have a quick one. So you threw down the gauntlet today of what I'm hoping is 3D printing glass. And the last time I heard you speak, and you didn't mention it today, was open source 3D printing electronics. So I was wondering, especially for the young people on the call, where you think we should put the most focus and the most effort to kind of bring the RepRap dream all the way through.
If I had the choice, I'd go for the electronics, simply because it's a more widely enabling. Can I believe I'm saying this? I'm about to say something that I'm not sure I believe. I think electronics is a more widely enabling technology than chemistry. Now, having said that, I'm quite happy for somebody to say the exact opposite, and I will not argue with them. But nonetheless, I'm sticking with it for a moment. I think that if I had the choice, I'd go for the electronics, simply because it would allow so many other things to be done so easily. But nonetheless, the chemistry, and in particular, as you say, 3D printed glass, there are 3D printing glass machines, though I'm not sure that any of them can be said to have made anything as complicated as the object that I showed. There are 3D printing glass machines, but it would, I think, be extremely useful for everybody working in the fields of, as wide as drug development, crop development, genetic engineering for improving crops, all that sort of thing, to have glassware that they can manufacture themselves in order to circumvent the quite astronomical costs that I showed you in the slide. Now, of course, I chose an example there which was particularly expensive in order to reinforce my point, but nonetheless, I just ordered a bunch of reagent bottles that cost me £8 each, and I'm sure they cost nothing like that to manufacture. So, you know.
Excellent. Thank you.
Excellent. I think I'll take speaker's privileges once again and ask you one question, since I have the grandfather of RepRap with us.
Made me feel old already.
Oh, only as old as you feel, so don't worry. What do you envisage as the next major leap forward in 3D printing? And do you see RepRap having a role in that as we move forward as a human race?
I don't know. I don't know what the future is. People often ask me to predict things, and I'm always very wary of prediction, because all the psychologists tell us that experts are hopeless at predicting things, because they very easily do studies. Of course, they go and find a bunch of experts, they ask them what's going to happen, they wait around for 10 years, found out if it happened or not, and sure enough it didn't. It's very tricky. What's the next thing? Well, going back to what Joshua asked me, I think that 3D printing electronics is something that would really make a difference, and I don't see any serious technical impediment to its being done, given all the equipment and bits and pieces that we have these days. And in particular, there's this general open source rule of how bad can something be and still be useful. In other words, going back to the Google open source design software, we don't need 130 nanometer chips from day one. We could do with much bigger chips with a much lower yield in order to implement things that were useful, particularly if we can get the cost right down. As I'm sure you're aware, the cost of fabricating chips is astronomical if you wanted to buy a commercial line for doing it. Things like ultraviolet etching machines, hard ultraviolet etching machines, are incredibly expensive. Circumventing that would really be quite extraordinary. Let me take a sort of 3D printing RepRap example or something like that. If you look at a commercial injection molding machine, which will produce hundreds of items a minute, those will cost $300,000-400,000. Of course, you can buy a 3D printing machine for $300 or $400, which means that you can buy 1,000 3D printers for the cost of an injection molding machine that will produce things, and perhaps not quite as good quality as the injection molding machine, but perfectly functionally good. You've got more robustness, because if one of them fails, it hardly makes any difference to your production. And you've got the ability to produce at more or less the same rate for more or less the same investment of capital. And the same is true with electronics. If you're going to make electronics cheaply using open source, possibly not as good as the commercial electronics current best systems are, you're still probably doing something useful.
Excellent, thank you for that, Adrian. I will have one more question, just in the interest of time. So, Fabio.
Okay. Professor Bowyer, thank you very much for your presentation. And certainly it's really inspiring the comments and the thoughts that you are working on. And I read your work a lot of time. One thing that I mess in my mind is that actually I believe, certainly I believe open source is a driver. It's a driver for technology. It's a driver for developing the competence for people for solutions. One thing that is struggle for me in my mind, in my research, is until what point technology is the solution? Until what point? What is the limit? For you, I don't know if you have comments about, because in the moment that we rely on technology, when electronics, we need to look for raw materials. We need to look for components that is not the time pass, we explode the natural resources. Until what point this notion of technology makes sense, if I can say? I don't know how to do it.
I think I understand. I think you say you don't know it, though. It's very eloquent. It depends if we go down the right path or the wrong path. As you say, if we make things by digging stuff out of the ground, there's a limit to how much we can do that, even if we engage in a certain amount of recycling. But if we make things using a combination of two things, which is one, completely circular technology, so everything we make gets recycled just as it does in biological systems. Well, almost everything we make gets recycled in biological systems. There are fossils, after all, those didn't get recycled. But if we mimic biology in our technology by having closed loops for everything, I don't see that there's a stopping point. There is a stopping point if we carry on doing things more or less as we do now. And of course, increasingly, not only will we be mimicking biology in order to make things, we'll be using biology to make things more and more, where what I've just said sort of comes for free. And so it's the case that I don't see a stopping point as long as we take the right path. If we take the wrong path, then either we'll be forced onto the right path by encountering the stopping point, or we'll end up going backwards when we hit it. So that's more a political and commercial decision than a technological one. We understand the technology of doing everything that I've just described, more or less. We don't understand everything about biology. We understand an awful lot. As I say, a bit like many of the problems that face us, it's not actually so much the technology is the problem, it's what the technology enables and what is then chosen by people, either in the political sphere or the economic sphere, because the technology could equally drive us, or rather be driven by those choices in the correct direction. So I don't know if that answers your question or not, but that's what I think.
Yeah, no, certainly. There is, because the thing is that you have more experience, so you have seen the transition between this transition. I'm just discovering this transition towards open source, but certainly the discussion is in terms of governance. So what we do with technology, and that Excellent. Is a little more complex thing.
Yeah, definitely, Fabio. But thanks for that question. It's a very interesting one. Please feel free to add further questions into the chat if you need to. Unfortunately, in the interest of time, we're going to have to move on to the next speaker, I'm afraid. But thank you once again, Adrian. It's been an absolute pleasure.
It's a pleasure. I'll be here till 3:30. I have another appointment then, so I apologize. But any questions that come up before then, I shall be happy to try to answer.
That's very good of you. Thank you so much.